Hi, my name's Evan, and today I'm going to share with you guys my investigation into compute shaders and specifically how they're going to be used for real-time computer graphics. Today I've created a pretty cool watercolor effect that runs in real time in Unity, hence the title Painting Without Paint. So what really inspired me was the fact that I really love making games, and something about computer graphics in particular is something that kind of, really excites me. So I use this project as an opportunity to explore a rather new technology in the space when it comes to computer graphics. So as a quick overview, what I'm going to do today is cover a quick overview of 3D rasterization. I think we need to cover this in order to kind of fully appreciate and understand compute shaders in its entirety. I will then go into an explanation about compute shaders, the problems that they solve, and how we interfaced with them as graphics programmers. Afterwards, I'll show how I used a bunch of compute shaders to create this cool watercolor effect in the Unity game engine, and that involved multiple passes of image processing, involving using the Sobel operator, doing this thing called the anisotropic Kuwahara filter, as well as a few of my own inventions. And then also I want to cover a little bit of some other exploration that I've done in compute shaders, which is my own frame-arched voxel engine, which I've been writing in C for a bit. So to the right here, what we see is a base render today, kind of the scene that I'm building out, and then the final effect that I'm going to be showing how, step by step, how I created it. All right. This here is it moving in real time. I get around 90 FPS on the scene on my computer. So 3D rendering. 3D rendering, what it really is just data crunching. We're taking data in the form of 3D models, letting information transforms, and we're turning it into a 2D image. We're crunching through that data, and generally that ends up being a pretty parallel task. It's not perfectly parallel, but it really does greatly benefit from parallelism. 3D rendering nowadays takes place in multiple stages, which I'll be going over today. As we've scaled up the demands of rendering, like the output resolution, the number of triangles and meshes that we're rendering, and then our general kind of expectations of visual fidelity, the development of specialized hardware, GPUs, took place, which is kind of the backbone of 3D rendering today. Today, you don't really see an old technology called software rasterization, which is 3D rendering on the CPU. It's just not commonplace, especially because GPUs are just everywhere now. So at the kind of core of rasterization, which is the most common technique of 3D rendering today, is the mesh. And mesh is what rasterization does is it basically projects it onto a 2D plane and then converts it into pixels and whatnot. So meshes, they represent 3D objects, and they do so by approximating the surface with a list of points. These points are ordered in such a way that they create edges, which then form faces in our mesh. It's important to note that they represent the surface of an object, not the inside. You can just put the camera inside of a mesh and you'll see nothing. And to build a scene, what we do is we assign these meshes individual transforms, things like a position, a rotation, and a scale, and then we place them throughout our scene to create a final thing that we can render. So in the standard rasterization pipeline, what we end up doing is we take the scene data that we read off the disk or something like that, we build it at runtime, and we put them into buffers on the GPU. This green box of scene data thing indicates that it is on the CPU. After sending it to the CPU, we do some to the GPU, we send it through this process of transformation. And this transformation happens parallel per vertex of the models and whatnot. And what this does is it takes that scene data, which is represented as some 3D stuff, and puts it into screen space, puts it into this 2D space that we can represent on the screen. It also generates a bunch of other things that are necessary for rendering. This is user configurable. We can write special programs for these called shaders. And this particular shader is called the vertex shader. There's a few other steps that kind of can take place. That's optional, but generally you just have the vertex shader. So this image to our right here shows that this 3D space in this step is being projected down into this 2D kind of image, 2D representation of points. Once we project it down to these 2D points, we do this process called rasterization. And rasterization, what it does is it takes these triangles that we had once had in this 3D space and projected it down into 2D, and we create these fragments, which are kind of tiny portions of the image. And nowadays, fragments are basically just pixels. This is done in parallel after completing all the transformations, and it's done specifically in hardware. You can't inject code into here. It is just how GPUs are made. There's no need to really inject code here. And after we've rasterized these into fragments or pixels, what we do is we send it into another kind of parallel user configurable program. And this program runs on each per pixel in parallel. And these fragments are colored per the user program. So that could be used to assign like, oh, this cylinder here, this is a red cylinder, and this has lighting, things like that per pixel lighting, and then placed into a texture buffer, which is ultimately returned to the CPU or just presented with the final image. This image to the right, I didn't touch on it, is what is known as a depth buffer, which is generated during this transformation step. And what that shows with the intensity of the darks and whites, how far or close objects are into our scene. So for a long time, GPUs were just made to do this exact pipeline. And GPUs still implement this exact pipeline. And we can interact with it using what's known as a graphics API. And common choices today are OpenGL, Vulkan, and DirectX. And these are direct abstractions over the GPU. Vulkan gets really into the weeds. OpenGL is kind of higher level. DirectX is kind of somewhere in the middle. And it's up to GPU manufacturers to support these standards. So we can see over to the right, we can see how NVIDIA kind of lays out their cards in hardware, and then how we can think of this pipeline as a user of graphics APIs. But with the advancement of computer graphics, and how parallel these devices were, non-graphics programmers kind of sought the SIMD capabilities of the GPU for more general purposes. But to do anything useful other than drawing triangles to a scene, drawing pretty pictures, we kind of needed to break out from this rasterization pipeline. Hardware needed to be made such that it isn't stuck on this pipeline, and then the APIs needed to allow for the user to interact with it in a more general way. And in 2006, NVIDIA released CUDA, which is the first kind of implementation of this idea. Following that, we had OpenCL in 2008, and kind of more recently, still a bit far back, we have OpenGL compute shaders and the Vulkan compute pipeline, which are the two things that I really use today, and it's commonplace when you want to do things within games. As most of the times the graphics APIs of choice for rendering, for rasterizing our game, tend to be OpenGL, Vulkan, or DirectX. So compute shaders. Compute shaders are basically how Vulkan and OpenGL kind of think about generalizing compute on the GPU. So what we do is we write these special programs called compute shaders, which we configure the GPU to run. They break away from the constraints of rasterization. They let you launch kind of arbitrary work items, sometimes called threads or invocations that don't necessarily have to write to a frame buffer. You kind of just call these programs by sending some data to the GPU, packaging it up, and then invoking them, dispatching them. And then kind of receiving the results later, kind of similar to MPI with how kind of the master sends out work to other parts of the clusters. And they're generally written in a shader language, the same shader languages used for traditional rasterization, like HLSL, GLSL, and then compiled for the GPU. So when writing compute shaders, as with every single kind of concurrency problem, you have to figure out what are your inputs and your outputs. And you need to package them up and send them to the GPU. You can kind of think of compute shaders as calling a really convoluted function, like calling it an extremely kind of really hardware-focused function. And it's important to architect both how you're getting your data, when you're getting the data, and what that data looks like when you send to the GPU. Afterwards, you can configure your GPU to use your compute shader, and that is done on the CPU side. And then finally, after packaging and sending that data to the GPU, we can dispatch the compute shader. So compute shaders go in work groups, which are three-dimensional, and these kind of you can optimize for different size work groups depending upon your problem space. Then finally, after dispatching it, you can kind of think about this as an asynchronous call. We grab that data from the GPU and put it into the CPU. So multipass compute pipelines kind of do this over and over and over again, and that's what I really explore today. So not every problem is solvable or best solved in a single pass. You sometimes need to do multiple iterations in order to create your final result. And it's common to feed the outputs of compute shaders into the inputs of another ones. And doing so does offer a lot of benefits. One, it offers a barrier to compute. Sometimes in order to to perform an algorithm, you need to ensure that this kind of part of computing the output is done. You kind of have to have that assumption, especially because we are working on a parallel system. We don't know if the other threads, the other workers are done with that step. And sometimes we need data from that. It also offers debugging information. So in tools like Unity, you could actually have like a frame debugger, which shows the outputs of all of the compute shaders, which kind of takes away from the black box of individual steps. And you also get less complexity per step on the compute shader side. Sometimes with having a lot of passes and a lot of steps, you end up kind of bulking up the CPU side, but that's kind of okay because CPU code is way easier to debug than GPU code. And for the purpose of kind of the effect that I made today, this was an absolute mandate. You could not do this in a single step, mainly because we need that barrier to compute in order to kind of move forward in our process. So let's cover up the pipeline I built today using compute shaders to create this watercolor effect. So the first thing I really did was kind of study what makes a watercolor painting look like a watercolor painting. And watercolor is kind of a medium where you really see the qualities of the material shine through. And there's a really obvious look to these paintings. And that's intentional. That one kind of really does water paint to look exactly realistic. If you wanted to do that, you'd probably go to some oil paint or other digital medium. We want to kind of show the beauty of the pigment and the material that we have. So a part of this is showing the individual directional brushstrokes in the painting. You can see kind of on the underside of the boat here, you can see where the artists kind of drag their brush around in order to create this shadow. Same here, and where parts of the pigment were thicker and thinner and whatnot. And generally, they have high levels of saturation because we're trying to show that we have good paint. A big quality of paint is how saturated it is. And because we want to show the qualities of our material, we generally, as watercolor painters, end up kind of oversaturating, showing how beautiful our paints are. And as a side effect, we also have kind of lower contrast because darker colors don't necessarily look the best. And we also generally use the white of the paper to show lighter portions of the piece. We can see in the flower that the opacity of the paint is lighter and we see the whites of the paper. We don't add white paint. We're simply making our paint more watered down. And because watercolor pigments, when you're painting, you don't necessarily mix them fully sometimes, or you do many, many layers, which is required for dark areas. You end up kind of getting these noisy dark areas, which you can see once again on the underside of this boat, on the top of the bird's wings, where they're a little bit noisy. And I think that's one of the greatest charms of watercolor right there. You also see this cloudy blending. You can see when the water stopped moving in the paint and dried up. Similarly, you can see these water lines where like really intense parts of the pigment kind of stayed there, kind of on the edge where the surface tension of the water ended, which is also a wonderful quality I would like to preserve in my implementation. So how do I break this up? This is kind of my own approach to creating this watercolor pipeline. I haven't seen anyone else do it quite this way. And also watercolor shaders are not really common. Painterly shaders is a very kind of specialized area of post-processing. So what I did was I used Unity to render the image in a traditional method, in this case, rasterization. And we took some information, like the normal buffer, which I'll show you guys in a bit, and the main texture output, the original image that the rasterization pipeline would produce for post-processing. Then following that, what I did was I added noises to the darker regions of the image to kind of hint at the fact that many layers are required to paint this darker region. Then I applied this really cool filter called the anisotropic Kuwahara filter, which gives it the painterly appearance. Then I applied what is known as the Sobel operator to draw kind of the pen and ink that is really common in watercolor. Generally, we do mixed media and draw kind of outlines of shapes because watercolor is loose and the pen helps us kind of bring and make our image a little tight. And also to draw those water lines I was talking about. Then finally, to get that kind of paper texture shining through, I kind of mixed the output of the pipeline thus far with a texture of a piece of paper based off luminosity, which is the brightness of each pixel, and added some paper edges. We can see here on this rightmost image this dark splotch of paint that was added from the noise of adding the darker regions, making that shadow a lot more kind of dynamic, kind of more interesting. And we can see the water lines next to this shelf. The shadow that the shelf casts has like this nice water line to it on some edges, where the contrast between the blue and the orange of the wall is really kind of present, where we're showing that. And we see the outlines in all three of these images. So the first stage, of course, is getting our baseline, getting the first image that we need to render, that we need to transform into a watercolor painting. So we use the traditional pipeline in the Unity game engine to do this. And we took the output, which I'm calling the main texture, which is above, the normal image without any post-processing, and also the normal buffer. I took those out in order to pass them into future stages. And I'll make note of which stages get what textures. So once we have that main texture, we can add the darker areas. So based off the luminance, which is the brightness of each pixel, I interpolate between this noisy texture and the original output. And lighter areas are unaffected. And at this stage, it's really subtle. We can see that the top image right here is what we're receiving into this pass, and the final image, the bottom image, is what we get after this pass. And you can see ever so slightly that the image is a bit darker, but also the darker regions have a little bit more color to it. It's kind of hard to see, but it gets really, really kind of enunciated when we go through this pipeline. So this texture to the left is what the texture I use to kind of blend these dark splotches of color between. And we can see that we're adding a bit of magentas, greens, and blues, kind of making the application of the paint look imperfect. And to the right is the compute shader. I won't go through exactly what the compute shader is doing here, but I'll point out a few things. We can see that there's a bunch of kind of uniform, just texture, these global variables. And these global variables are passed in through the CPU side. They're packaged by the CPU and sent in. So it's kind of being expected. This is like an input of our system. We can also see that we have this number of threads attribute up here, which shows like the work group size, kind of, this is kind of an area of optimization. And we can see at the bottom, what we have is we're writing kind of the ID of the thread. And the ID of the thread can kind of be thought of in this sense as the individual pixel. It's not always necessarily the individual pixel, like the 2D index of the pixel. It just so happens it is here because that's how I configured it on the CPU. This index can be anything, but it is a nice way to kind of differentiate and store the results of each parallel process that happens on the GPU into a different place, maybe calculate something differently because of that. Stage 2 is where it gets kind of interesting, where we add the anisotropic Kuwahara filtering. And this is kind of like a weird like statistics thing, but in effect, what this filter does is it results in a painterly appearance where kind of brushstrokes are aligned with the flow of the surface. And the flow of the surface is given to us by the normal texture. And the normal texture, which is produced by the rasterization and pipeline that happens way before this, basically says what direction in 3D space is this pixel looking at. So we use that to kind of figure out the flow of the surface. And this happens in a very similar way to contrast stretching, where we grab kind of a squarish window, which is called a kernel in this sense. And we divide it into a bunch of regions, and we calculate the mean and the variance of each of the pixel intensities within the regions. And then we assign whatever pixel we're looking at the mean of the quadrant with lowest variance. So what ends up happening is that regions within the same kernel end up kind of looking like the same color. And it's not an exact square window like we see with contrast stretching. We use the flow to kind of like move the kernel around. I'll show what I mean by the next picture. But what ends up happening is because we're kind of squishing and stretching the kernel around, we end up preserving edges in flatter regions and things like that, and give that directionality to the brushstroke. So we can see here, this is the research paper where the technique was discussed that I got this from, that in this original image, we have this lion, but after applying the anisotropic Kuwahara filter, we can see that kind of clumps of color end up kind of assimilating, and there's a clear flow to it, especially in the lion's mane. we can see how the kernel, they use a circle kernel in theirs, kind of stretches along edges versus flat planes based off the flow of the image. So the third stage in this effect is applying what is known as a Sobel operator. So the Sobel operator is a convolution of two matrices over the image. And what this operator does is it really just highlights areas of contrast in the image. Once again, it is an effect where we have a kernel and we're grabbing a kind of box of the image. In this case, I use a 3x3. So 3x3. We do it once on the depth texture, which is very similar, which is a texture I pointed out earlier, the normal buffer, in order to figure out where the pen and line is. And kind of the intuition behind that is that generally you'll draw lines at the edges of objects, which would be detected by the depth textures, the result of convolving it with this matrix. And the normal buffer would give you kind of the edges within the object. And then we also do it once on the main output texture, which would highlight areas of contrast within the colors that we've done so far. And that is basically the water lines, those areas of high contrast. I really want to show the edges of the water. So we can see to the left, what we have here is we have this original image, and this is the result of applying the Sobel operator. We can see that the whites are where kind of the edges of the images, areas of high contrast have been highlighted. And you can see the output code here of the compute shader that I wrote. Finally, what I wrote was to add this paper texture to it. So we use the luminance, which is once again the brightness of each pixel. So this runs on a per pixel parallel thing, to map the brightness, map the color of the pixel to some kind of paper texture that I pass into the GPU. This has the effect of having lighter areas looking more like the texture that I passed in, which kind of shows the opacity of the paint. I also use a mask to show kind of as part of this interpolation, in areas of the mask that are black, what ends up happening is that I force it to be paper, which kind of gives imperfect edges on the edges of the paper. Because when you're painting, it's sometimes hard to apply paint in the edges. So to the left here is my mask that I made in Krita, and to the right here is a paper texture. And this is a pretty straightforward compute shader that I wrote and dispatched. So afterwards, Unity does some additional post-processing that they do with their own traditional method, not with compute shaders, and that I just kind of tweak around per seed. And we end up with this final image. The workload here ends up kind of bouncing back and forth between the CPU, which is not the CPU and GPU, which is not necessarily a good thing. In modern computers, kind of the bottleneck here is the communication between the CPU and the GPUs. That's really slow, simply because they're really far apart compared to individual like parts of the CPU or GPU. But it's okay. You know, for my machine, which has a laptop RTX 3060, I got like 120 FPS on the scenes demoed. But luckily, because we're kind of running this algorithm on a per pixel basis, this doesn't affect the speed of the algorithm depending on the complexity of the scene, the amount of triangles, the amount of models that we have. However, if I were to scale it to 4K, that would be absolutely disastrous. I'd probably get like 20 FPS. So what's better to demo a watercolor shader than some water I wrote? This is a nice little water effect that I created using this thing called Gershner waves. It's a pretty straightforward implementation. But yeah, I find the effect quite beautiful, and I'm very happy with how it came out. So I showed you one application of compute shaders, but there are definitely way more than that. Compute shaders are limitless. Right here, I showed you an instance where I use compute shaders to build a post-processing effect, doing some image processing stuff, where I'm transforming a bunch of pixel data to get more pixel data. But compute shaders, as I said before, are really just convoluted function calls. You can theoretically just like call them for anything. You can do them with ML, data processing, simulation, game AI, things like that. But from what I've seen on the internet, maybe it's possibly because of what circles I'm in, people generally use them for game AI with a lot of like kind of agents or this type of graphics processing. So I've used the compute shaders in the past. I won't lie, this is not my first exploration to compute shaders. However, it is my first exploration into kind of chaining them together and creating kind of a way more complicated effect than I've seen before. So we can see here in this game that I was working on once upon a time, I used a compute shader to create a very, very subtle effect where objects, little objects, when they were hidden behind something, you got this little silhouette, which helped the player read the scene better. And instead of being fed like pixel information, the depth and normal texture, this was fed information like the position of entities, their rotation, and their individual sprites, as well as like kind of a mask showing the depth of the scene at certain points. I've even used them to do very simple things like pixelating games for the aesthetic. We can see here that on the top, the image is a little crunchy, which is a nice visual effect. And on the bottom here, similar, same here. And this is an extremely simple compute shader to write, especially within Unity, and probably the go-to if you're trying to learn compute shaders. And finally, I've done a bit more of an exploration into just only using compute shaders. Before, I've kind of used them to like be paired with Unity and the traditional rasterization engines. But I had an idea this past January where I was like, you know what if I don't need to rasterize things? I can simply just write my own game engine in C. I'm specifically using the 1990 standard with a very low-level graphics API called Vulkan. and I'll just do everything from scratch, which is a terrible idea if you actually want to make a game. But I like making game engines apparently. So this engine, which I'm calling Raxel, is very different from traditional game engines because we don't use meshes in Raxel. Instead, we have a 3D voxel grid, kind of similar to Minecraft, and this allows us to make objects with volume inside of them. We're not approximating the surface of things, but also having some internal volume. So you can imagine I can break into this object, break into these spheres, break into this poor rendering of a voxelized sphere, and see stuff in it. So yeah, there's no rasterization here. It's built entirely on this big uber mega compute shader, and the CPU feeding it a lot of data. Thank you so much for listening. I hope I informed you about compute shaders and specifically how they can be used in game dev, but also hopefully more generic environments. Thank you.